take it away.
Hi everybody, I'm John and I'm a philosopher, and this is a collaboration with two cognitive neuroscientists, Ben and Nico. Neural networks can be hard to understand, but the algorithms we use in cognitive science are often easy to understand. It would therefore be helpful if we could identify a mapping from neural networks to these algorithms that let us use the algorithms to better understand neural networks. In cognitive science, we use algorithms to explain a wide range of behaviors. We use tree search to explain chess moves. We use the column method to explain addition. We use reinforcement learning to explain foraging. We use Bayesian inference to explain decisions about orientation. We use sequential sampling to explain decisions about the direction of motion. In this talk, I'm going to focus on an extremely simple example. Suppose we train a network on the mapping from x to 2x plus 2. There are at least two algorithms that a network could use. First, it could take the input, multiply it by 2, and add 2. Alternatively, it could take the input, add 1, and multiply that sum by 2. How can we determine which of these algorithms a network is using? Traditional methods are parts-based. Parts-based methods look for network parts that correspond to algorithmic parts. The relevant parts, for example, might be activations. For example, the activation of a particular neuron or node, a layer, or across multiple layers, or even subspaces of that activity. We might find one part corresponding to times 2 and a later part corresponding to plus 2. In that case, we might infer that it's implementing 2x plus 2. Alternatively, we might find an earlier part corresponding to plus 1, a later part corresponding to times 2, and we might infer it implements 2 times x plus 1. The relevant parts can also be weights, and once again, we can find parts that correspond to the relevant parts of the algorithm. We can conclude which algorithm it is implementing. This method has had a number of important successes. They include path integration in the fly, sound localization in chickens and owls, central pattern generation in rodents, sequential sampling in macaques, and feature mapping in humans. In artificial networks, there's also successes for modular arithmetic and natural language inference. But there have not been as many successes as we might have hoped in the neuroscience case despite decades of research. This has led some to conclude that we shouldn't try to understand neural networks in terms of science algorithms. Just as we discovered that there is no such thing as phlogiston, according to these thinkers, we have discovered that neural networks rarely, if ever, implement cognitive science algorithms. In an attempt to save cognitive science algorithms, we wish to explore a different method. Our method centers on learning speed. Learning speed is an important method in cognitive science. For example, Tolman used learning speed to infer that rats had cognitive maps of their maze. In particular, he found that rats that randomly walked around their maze were able to faster learn their way back to a reward, and he inferred that meant they must have a cognitive map. Learning speed is also important in machine learning and in computational neuroscience. We wish to use learning speed to recover a network's algorithm. Returning to our toy example, if a network implements 2x plus 2, in order to learn this first mapping, it only has to make one change. It only has to change its coefficient. In order to learn this second mapping, it has to make two changes. It has to change both its coefficient and its constant. In contrast, in order to learn 2 times x plus 1, if it was implementing 2 times x plus 1, it only has to make two changes to learn this first mapping, and it has to make only one change to learn this second mapping. We would therefore expect that if it was doing 2x plus 2, it'll be faster at learning the first mapping than the second, and if it was using 2 times x plus 1, it will then be faster at learning the second mapping than the first. And we can thereby use relative learning speeds to recover which of the algorithms the network had originally learned. To put this to the test, we trained 300 very simple networks, and then we trained them on a series of fine-tuning functions. This network learned the blue line faster than the orange line. That is, it learned 4x plus 2 faster than 4x plus 4. It took less data for it to be better at learning this mapping. And this wasn't a random result, it was systematic. So it also learned 8x plus 2 faster than 8x plus 8, 12x plus 2 faster than 12x plus 12, and so forth. So on the learning speed method, we infer that this network implements 2x plus 2. This other network, however, learns the orange line faster than the blue line. And this again was systematic. It learned all the orange lines faster than the blue lines. It learned 8x plus 8 faster than 8x plus 2, 12x plus 12 faster than 12x plus 2. So on the learning speed method, we infer that it implements 2 times x plus 1. Out of our 300 networks, 9% implemented 2x plus 2, and 61% implemented 2 times x plus 1 for an overall interpretability of 70%. Now you might be wondering, are these categories introduced by learning speed already evident from parts-based methods? And the answer is no. So first we looked at performance, and we found that they did not correspond to accuracy on the training domain, on a nearby domain, or on a more distant domain. It also didn't correspond to the clustering that resulted by looking at error patterns. We then looked at activations, and we found that we could not linearly decode these categories from the activations. We also found that these categories did not correspond to the RSA similarities. Next, looking at weights, we found we couldn't linearly decode them as well, and once again, these categories were not evident through weight similarity analyses. For the full, for the full analyses, I hope you'll come see the poster. But you might wonder, maybe this is just such a simple, stupid task. So then we looked at some slightly more complicated tasks, one involving 2 variables and the other involving a nonlinear function, and we found the same pattern. Okay, but then you might wonder, maybe this is just some fact about algebraic tasks. So we next looked at an experiment involving image categorization. We trained 10,000 images from 4 latent variables. Those variables were shape, area, object color, and background color. We then assigned the images labels that were based on these latent variables. In order to learn this task, a network would need to learn how to estimate each of these latent variables. With respect to shape, we put all of the shapes into 2 groups and assigned each group a value. There were thus 2 different algorithms a network could use to estimate the shape value. First, it could learn to detect all the shapes in a group together at once without distinguishing between the individual shapes. Alternatively, it could separately detect each of the shapes and then separately assign them the relevant value. In order to tell these 2 algorithmic hypotheses apart, we again looked at learning speed. We created a series of different fine-tuning functions. The first fine-tuning function, we took the same shape groups, and we took one shape from one group, another shape from the other group, and we switched them. Another fine-tuning functions, we just took 2 of the latent variables, and we inverted their values. If a network was using joint detectors, it should find the first task relatively hard because it needs to learn to distinguish between shapes that it was previously not distinguishing between, that were previously entangled for that network. Whereas it should find the second set of fine-tuning functions relatively easy because given the nature of the task, it already had to learn how to distinguish these latent variables. For the separate one, though, it should find them both relatively equal because they're all the same. So we would expect the reverse shapes to be slower and the second to be faster. In the case of separate detectors, we'd expect to find the same speeds. So we trained a bunch of 60 convolutional networks. We found some networks found the reverse shapes fine-tuning function much harder. So in our analysis, they implemented joint detectors. We found other networks that found them just as hard. So in our analysis, they implemented separate detectors. And overall, we found 40% and 38% of the networks were categorized as either having joint shape detectors or separate joint detectors. Once again, you might wonder, are these categories already evident from parts-based methods? And the answer is no. We didn't find them by looking at performance, by looking at activations, and by looking at traditional analyses of weights. You might wonder, are these tasks just too simple? So we looked at 3-dimensional images, and we looked at both linear and nonlinear mappings on those and found the same results. So finally, the last slide, I swear. We're trying to find a mapping from neural networks to cognitive science algorithms. Our proposal, in general, is that we define a space on cognitive science algorithms by basically looking how much you have to change one algorithm to turn it into another, and that gives you a sense of distance. We also define learning speed distances by looking how long it takes a network to learn different input-output mappings, and that gives us the ability to find mappings between them, and that's the right way to line up cognitive science algorithms with neural networks. Now, I'm sure many of you have a lot of questions about this general framework, so please come see me at the poster today. There's going to be a preprint coming soon. It'll be posted on my website. And I just love talking about this stuff, and I love talking to cognitive neuroscientists, so please feel free to reach out whenever, either at this conference or shoot me an email later. Apologies, sorry.